So welcome everyone for the to the virtual commutative algebra seminar of IIT Bombay. We are very happy to have Tai Ha from Tulane University. Last time we saw him in Mumbai when he was visiting faculty in our department, and we thought he will come back next year, but we have to see him online. In any case, thanks Tai for coming online and preparing this talk for all of us. So, so you may now start your lecture on the ideal containment problem and vanishing loci of homogeneous polynomials.
Thank you, Juga. Thank you for the invitations and for giving me the opportunity to visit you guys again virtually this time, unfortunately. Hopefully it's going to be in person again sometime real soon. So the talk today is based on two recent joint work that I wrote with Sankanil Bisui, Eloisa Griffith, and Tai Nguyen. Eloisa is from the University of Nebraska in Lincoln, and Sankanil and Tai are my PhD students, and let me do a bit of advertising here. And Sankanil is graduating, he's looking for a job, and he's really, really good. Okay, so the title of the papers that I'm going to talk about is slightly different, quite different from this, so I try to put a twist and a little bit of new motivation to the problem, so I use this title. So let's start with the motivations, and the motivations of the study comes from the polynomial interpolation problems, and the polynomial interpolation problems start with a very simple fact that a polynomial in one variable is completely determined by its zeros. Slightly more generally, if we give an S point on the alpha line and S positive integers sum up to d plus 1, where d is at least S, then a polynomial of degree d is completely determined by d plus 1 vanishing condition on its derivatives. So the condition is the chase derivative of f evaluated at xi is 0 for all I running from 1 to s, and all j runs from 0 to mi minus 1. So equivalently, if we form the matrix given by these vanishing conditions, treating a0 up to ad as our parameters, then we would have a d plus 1 by d plus 1 matrix, and the condition the statement that this polynomial is uniquely determined by the vanishing condition is really the same as saying that this matrix is of maximal rank. So, of course, the question is what happened in higher dimension, and that is the relation, or that is where the polynomial interpolation problems comes into play. So before studying the problem, let me fix some notations. Throughout my talk, the field is going to be the complex numbers. A lot of what I'm going to say are actually true for the field, but just to be simple, let's keep the field to be the complex numbers. If I write Pn without any index or subscript, it means the projective n-dimensional over the complex numbers, and bold X means denotes the collections of coordinates of Pn, and R is the coordinate ring of Pn. X is going to be always denote a set of points, P1 up to Ps in the projective n space, and M1 up to Ms will be positive integers. So the polynomial interpolation problems can be stated as follow. Given a finite set of points and positive multiplicity, find the number of homogeneous polynomial of a fixed degree d in this polynomial ring that vanish at each pi of order at least mi for all I runs from 1 to S. So there's a way to understand this problem through ideal theory, thanks to the famous Zariski-Nagata theorem. So let me mention it here. So if we start with a point, pi here, then there's a prime ideal. So it corresponds to a prime ideal inside the polynomial ring, and of course the set of point will correspond to the intersection of these prime ideals. We can look at points with multiplicity. In other words, we can look at M1 copy of P1 up to MS copy of PS. And one way to write that is the collection Y equal to M1 times P1 plus up to MS PS. This is what's usually called a fed point scheme. And the defining ideal of this variety is going to be P1 to the M1 intersect up to PS to the MS. And basically, in a nutshell, Zariski's Nagata theorem says that if you look at the degree D piece of the defining ideal of this fed point scheme, you get exactly the homogeneous polynomial of degree D, that vanish at pi of order at least mi for all I. And so the polynomial interpolation problem is really about a problem about Hilbert functions. So here I'm using H of an ideal and D to indicate the dimension of the degree D piece of the ideal, or I can just look at the Hilbert function of the variety and let Hy D to denotes the dimension of the quotient ring of the polynomial ring by the ideal. And so the question is, given X, given the multiplicity, what is the dimensions of the ideals of Y in degree D, or what's the Hilbert function of the variety Y in degree D? So this is basically is the question about Hilbert function of fed point scheme, and this question is of course largely open. The answer, a satisfactory answer, is only known when one has less than or equal to 9 points, for example. If there are more than 10 points, then the problems is extremely hard. So even in special situations where all the multiplicity are the same. So in the equi-multiplicity case, we assume that M1 up to MS are the same, and let M be these common values. Then we can write Y as M times X for short notations. And in this case, the ideal of Y happens to be the M symbolic power of the ideals of X. I'll come back to this more later when I talk about the containment problems of ideals. It's a very basic fact about Hilbert functions of point that the Hilbert functions of Y. So Y is of course a degree dimension 0 variety. So its Hilbert functions eventually is equal to its Hilbert polynomial, which is a constant, and that is the multiplicity of the variety, which is in this case S times n plus m minus 1 choose n. And so the Hilbert function is at most the dimension of the ring at degree D and its multiplicity. And in general, we expect that when we expect that when the supports are general enough, things are as nice as we can hope for. Particularly, we expect that when the points in the support X are general, then we should have the equalities. That's the Hilbert functions of Y at degree D is exactly the minimal number, the minimal between these two numbers. In other words, we know exactly how many degree D polynomials that vanish at the point in X with multiplicity at least m. However, this is a very difficult fact to prove. For instance, in a series of 4 papers or so in the 90s, Alexander and Hershkovich prove what we expect only for the case when m equal to 2. So the multiplicity is 2. That means we're looking at double points. So the theorem is that if we start with a collection of S general points in Pn, and Y is the collection of double points supported at X, then Y has maximal Hilbert functions with the following exceptions. Either we have quadratics, and the number of point is at most the dimension of the space, of the ambient space, or we're looking at cubics, 7 point in P4, or we're looking at quartic, and say if n is 2, then we have 4 choose 2, so 5 point in P2, or n is 3, we're looking at 9 point in P3, or n is 4, we're looking at 14 point in P4. Right? So those are the only exceptional cases, and outside of these exceptional cases, we indeed have what we expect. I mean, the Hilbert function is or maximal Hilbert function. And this is only for the case where the multiplicity is 2. Okay. Let me also mention, in case if you're students and you read in the literature and you run into this different problems, that the Alexander, I have a misspell here. The Alexander-Hershkovich theorem can be stated in terms of the expected dimension of secant varieties of the Veronese variety, or the Segre-Veronese variety, or the Waring rank problem for general homogeneous forms. For higher multiplicity, or meaning m is bigger than 2, at least in P2, one also expects that generally it is as what we expect with a list of exceptional cases. And there's a conjecture called the SHGH conjecture that predicts what is in this exceptional lists. SHGH here is for Serre, Harburn, Gimigliano, and Hershkovich. Okay, so let's focus on, from now I'm going to focus on a much weaker problem. So here we're looking at, the Hilbert functions, right? We want to find out what the Hilbert function is. Now let's look at a much weaker problem that asks, when is this Hilbert function non-zero? So when are there polynomials inside the degree D piece of this ideal? Okay. And so so for that, I'm going to let alpha denotes the least generating degree of a homogeneous ideal. That means it's the last, it's the smallest place, the smallest degree at which the Hilbert functions is non-zero. And the problem that we are focused now is not about computing the Hilbert function, but rather addressing a simple question that when is the Hilbert functions, when the Hilbert functions start to be non-zero. Okay, so the problem is if we fix a number of a collection of points and a multiplicity, what is the least degree of a homogeneous polynomial that vanish vanishes at those points with order at least n. Okay. So this problem, even it is the simplest case of the polynomial interpolation problem, is still a very difficult problem. There are a number of conjectures that I'm going to mention now about these values alpha of the m symbolic power of x. And the first conjecture is the famous conjecture by Nagata, which states that if x is a general set of points, of S points, then alpha of Ix symbolic power m over m is always at least the square root of S. And he actually proves this when S is a perfect square. So it's open when S is not perfect square. Now, when the set of point is not general, when X is not general, of course, one expect that this invariance depend not only on the number of points, but also on the configuration of the point, right? On X itself. And that is reflected in the conjecture made by Chudnovsky. Chudnovsky conjecture that if you take any set of point instead of general set of point, then this quantity alpha of Ix to the symbolic power m, the least degree of the polynomial, the least degree that we're looking for over m is always bounded by alpha of Ix itself. So the least the least degree of a homogeneous polynomial that vanishes at the point in X plus n, which is the dimension of the ambient space, and here ions minus 1 over n. And for the purpose that we're going to see later, I'm going to remark here that n is the codimension, or is the height of the ideal defining the point. Okay. Dimai later on generalized Chudnovsky's conjecture in saying that, well, the same quantity that we are having on the left-hand side here is bigger to, on the right-hand side, we have similar quantity, except now instead of just alpha of Ix, we look at alpha of the t symbolic power of Ix. And the numerator, of course, the denominator also changes with t. And when t equal to 1, right, when t equal to 1, you just get back the Chudnovsky's conjecture. So the focus of our work is actually on these two conjectures. There are a lot of work on this conjecture, on the Nagata conjecture still, but we are not looking at that. So I'm not going to say anything more about Nagata's conjecture. For the rest of the talk, I'm going to focus on this conjecture, Chudnovsky and Dimai's conjecture. There's a way to state this conjecture with if you look at this conjecture, one can see that the right-hand side is a fixed quantity given x, and here we also consider it as a fixed quantity given x and given t. This, of course, depends on m. So there's a way to state this conjecture for all m based on what we call the Wahrschmidt constants. And the Wahrschmidt constant for a homogeneous ideal is defined exactly to be the limits of the quantity on the left-hand side that we are interested in. It's not trivial, but it's known that this limit exists. That's rather easy. N is the infimum of all of them. So because it's the infimum of all of them, so we have equivalent statement for the conjecture in terms of the Wahrschmidt constants. So again, when x is any set of point in Pn, then Nagata says that if x is general enough, then alpha hat, which is the Wahrschmidt constant of Ix, is at least root of s. In fact, it's already known that alpha of Ix is less than or equal to root of S. So so Nagata's conjecture is that when X is general, one indeed has the equalities. And Chudnovsky conjecture say that the Waterschmidt constant is bounded by this quantity, and Imai just say, well, the Waterschmidt constant bounded by this quantity when you replace alpha of Ix by alpha of the t symbolic power of X. So what is so let me state the results that are known for Chudnovsky and Imai's conjecture. There are many works about Chudnovsky's conjecture. It's known to be true for points in P2, and this is due to Chudnovsky himself and a later work by Esno and Vivek. It's known to be true for general set of points in P3. This is due to Dumnisky. For n+1 general points in Pn, again due to Dumnisky. For points forming a star configuration, we're going to come back to star configurations later on by Bokshi and Haburn, by Giuliano, by Giramita, Haburn, and Migliore. It's true for points lying on a quadrix by Fowley, Montero, and C. It's true for very general set of points by Dumnisky, Tatar, Gazinska, who proved the statement for at least 2 to the n point, and by Fowley, Montero, and C, who proved the statement for any number of points. And let's put in the same context. The result that I'm going to talk about today is our results where we prove the conjecture is true for a general set of points, general set of at least 4 to the n point in the end. Less is known for the Imai. For P2, again, is true due to the work of Esno and Vivek. And if we fix T, is known to be true for very general set of points by Malara, Remberg, and Spond, and then a slight improvement by Chang and Zhou. Another theorem that we have is to show that the Imai's conjecture is true for at least for a general set of at least 2t plus 3 to the n points in Pn. So here you
question.
Yes.
What is the meaning of very general set of points?
That's a great question, and exactly what I'm going to get at, right? So here you see the statement with the general, very general. So what exactly does it mean? Now, usually general set of points and very general set of points are defined by looking at a Hilbert scheme, right? So if you fix number of points to be S and looking at all the collections of S points in Pn that form a scheme that's called the Hilbert scheme of S point. And when you say that something's true for a general set of point, that means there's an open subset of the Hilbert scheme such that whenever your set of point is inside that open subset, then that property holds. Very general set of point means instead of having one open subset in the Hilbert scheme, you now have countably many open subsets, and you take the intersection of that. Okay? Now, there's a slightly easier way to see the statements of when a property holds for a general or very general set of points instead of going through the Hilbert scheme, and I'm going to talk about it here. So here we start with the set of point X being P1 up to PS. And let's write down the coordinates of this point. So if P1 is A10 P up to A1n, P2 is A20 up to A2n, etc. PS is AS0 up to ASN. Then X is completely determined by this matrix. If I put the coordinate together, I get an S by n+1 matrix. And I can actually, I'm going to see or view this matrix as a point in this parameter space, in the affine space of dimension s times n+1 in a parameter space. Okay. So now, if we start with a collection of s times n+1 new indeterminates, so that's Zij. Again, I'm looking at in a matrix form, and I'm looking and I let Cz be the transcendental extension of the field C by this new indeterminates. Okay, then we can look at the points, which I denote by Piz, whose coordinates are just this new indeterminates, right? So the ith point is going to be Zi0 up to Zin. And this is a point inside the nth dimensional projective space over this extended field. So the set of this point, there's only one of them, is called the set of S generic point. And generic point here is inside this projective space with the field already extended. Now, there's a way to go back from this generic point to the point that we start with by substitution, by substituting A for Z, or by setting Z ij to equal to Aij. Now, of course, it's not always the case that if you take any A inside the space, the parameter space, if you take A in here, it's not necessarily that the resulting collections is a set of points or is a set of distinct points in our projective space in Pn. However, it's very easy to see that there's an open then subset W0 such that if you take A to be inside W0, then the resulting sets after the substitution Zi Aij to for Zij is a set of S distinct point in Pn, and in fact, all set of S distinct point in Pn comes in this way. So Pauli, Montero, and C basically proves that the following is an equivalent definition for being general and very, very general. The property P is said to hold for a general set of points if there's an open dense set of points in Pn, if there's an open dense subsets in the parameter space such that P holds for Xa for all A in this open dense subset. And P is said to hold for a very general set of points if there are countably many open dense subsets UN in the parameter space such that P hold for X of A whenever A is inside the intersections of this countably many open dense subset. So that answer your question, right, Jugan?
Yeah, it does.
Okay, great. Okay, so the difference between general and very general is, on one hand, you actually have one open dense subset that works for all powers. As we'll see later on, we have to work. We have to look at the inequality for or containment for one power at a time. And very general means we look at one open subset that works for one power, and then in order to get the statement for all power, we have to take the intersection of all these open dense subsets. Okay, let me switch gear and start talking about the containment problems. That's part of the title of my talk. So let me remind you, especially for the new graduate students, that for an ideal in a polynomial ring, in a ring in general, the M symbolic power of I is given by looking at the first the extensions of the M power of I in the localization of R at P, and then contract back to R when P runs through the associated primes of I. Now, there's a slightly different notation or definition that use the minimal primes instead of associated primes. So to avoid any discrepancies, I'm going to focus on radical ideals. And for radical ideals, there's no difference between these two definitions, particularly for the defining ideal of a set of points. So let me remind you that X is a set of points, P1 up to PS. Each of them correspond to a prime ideals. And the defining ideal of Ix is just the intersection of these prime ideals. This is radical ideals. Y being Mx is the same as saying that the ideal of Y is P1 to the M intersect up to PS to the M, and that is the same as by definitions, the M symbolic power of S. The containment problems for ideal originated from this very well celebrated results proof in the early 2000s by I. Lassersfeld and Smith in characteristic 0, and by Hochster, Hunicke in for positive characteristic. And the theorem says that if we start with a radical ideal of big height, H, in any regular ring, then for all R bigger than or equal to 1, the HR symbolic powers of I is contained in the R ordinary power of I. The containment problems is to improve this bound. So there are two ways of improving this containment, right? To improve this containment, there are two ways of improving this containment. One can either make the left-hand side bigger by dropping the power, or make the right-hand side smaller by multiplying an ideal with an ideal, right? And for that, there comes two conjectures. The first one is due to Harburn, where he conjectured that one can drop this power by h minus 1. So he conjectured that the hr minus h plus 1 symbolic powers of I is contained in the R ordinary power of I. Now, it's very easy to see why this is the best that one can do. In fact, without this one, there are a lot of known examples where this containment fails, and there's reason for why the containment should fail. And then there's conjecture by Harburn and Hunicke, which says that, well, if you keep the left-hand side fixed, then one can make the right-hand side smaller by multiplying with an appropriate power of the maximal ideal. Okay, so I of the HR symbolic power of I is contained in M to the power R times H minus 1, I to the R. And one can also write a more general containments of the same form, incorporating the symbolic powers of I also on the right-hand side. So the containment say the R times T plus H minus 1 symbolic powers of I is contained in, still get the same power of M to the R times H minus 1. And we look at the T symbolic powers of I raised to the power R. Now, the good thing about this containment and what motivate us from studying this containment is that the Harburn-Hunicke containment implies Chomsky's and Demey's conjecture. Now, often I was told that when I give an hour talk, I should do some proof. So I'm going to do a proof of this fact. Okay, it's quite simple. Let's say we have this containment, and in fact I should mention here is we have two containments, right? One is the simple form, and I'm going to say I'm going to refer to this as the simple form and as the strong form. Okay, Haber-Hunicke containments. You see that if instead I look at the simple form, I will get Chudnovsky's conjecture. If I get the strong form, I will get Demey's conjecture. Okay. All right. So suppose that we have the strong form of this containment that basically say that the alpha invariance of the smaller ideal has to be at least alpha invariant of the bigger ideal. And so the right-hand side is known. First, alpha of this come from this power of m. M is generated in degree 1, so the r times h minus 1 power of m is generated in degree r times h minus 1. And then alpha of a ordinary power is just r times alpha of that, of the ideal, right? So we have this quantity, and now we divide both sides by this power by r times t plus h minus 1. Then we kill off the r, and on the right-hand side, we have exactly alpha of the t symbolic power of I plus h minus 1 divided by t plus h minus 1. So h here, let me remind you, is the big chi of the ideal, right? And so in our case, big chi of the ideal, a point is n, okay? Now, if we take the limits as r goes to infinity, then because the Wahrschmidt is known to exist, we know that the Wahrschmidt constant is at least the right-hand side. And now if you replace h by n, which is the dimension, the height of the ideal of points, we get exactly what Demey's conjecture states. Okay, the bad news is counterexamples to Haber's conjecture exist due to first from the work of Dunsky, Zemberg, and Tatar-Garzinska, and then Haber and Siciliano, and then since then there are various different papers giving various different counterexample to the Haber's conjecture. Let me also mention here is that the simplest situation for Haber's conjecture is when the ideal is of big height 2 and the value r is 2. So we are looking at the containment I symbolic third power contained in maybe right here, I symbolic third power contained in I squared. And those counterexamples say, well, for given particular ideals, it fails this containment. The good news, the good piece of news is, and of course, if there are counterexamples for Haber's conjecture, one might expect that there should be there could be counterexample for the Haber-Hunicke conjecture as well. However, that is not known. No known counterexample to the Haber-Hunicke conjecture are available yet. The good news is to establish this Chudnovsky and Demey's conjecture, as you have seen at least in this proof, that we are taking the limit as r goes to infinity, right? So all we really care about is that limit exists, and there's the inequality for the values of r somehow in a subsequence that we can take a limit of, right? So in other words, all we need is the containment, the Haber-Hunicke containment for infinitely many values of r. And that leads to naturally to the study of stable containment instead. So instead of asking for containment for all values of r, we're now asking for the containment for all r big enough. Okay? And so the stable Haber containment basically now asks this, asks the same containment as before, except that we have the condition that this is true for all r big enough, and similarly for the Haber-Hunicke containments. Now, clearly, all the known counterexamples will not be counterexample to the stable containment because they are counterexample specifically for the first containment, okay, for I to the third, symbolic third not contained in I squared. Okay, so now let me state all the theorems in our papers. The first theorem that we prove is that the stable Harborne conjecture holds for the ideal of any general set of points in Pn. And the stable Harborne-Hunicke conjecture holds for the ideal of at least 4 to the n general set of points in Pn. And that's why we get Chudnovsky's conjecture for at least 4 to the n general point in Pn. The Harborne-Hunicke containments, the strong version of it, hold not for all large enough value R, but for an infinitely, at least for an infinitely many values R, if we look at the ideal of at least 2t plus 3 to the n general point in Pn. And so we get the Maillet's conjecture for at least 2t plus 3 to the n general point in Pn. Okay. So let me now describe our method. And actually, this is not new in this area of work. People have used this method before. One of the general method that we use and people have used before is by specializations. And the techniques of specializations goes back to Krul in the 40s. And Krul define a specializations with respect to a parameter A inside a parameter space to be a map, which we denote by pi of A, from the set of ideals inside the polynomial ring with coefficients being this extended field to the set of ideals inside the polynomial ring with coefficients being the complex numbers. And the map is given by, you start with an ideal in here, okay? We look at all elements of that ideal, which are honest polynomial in both x and z, in both the variable x and the new indeterminate z. And then we do the substitutions A for z. Okay. Now, so even though it looks kind of simple, one has to pay special care when working with specializations. For example, specialization or specializing an ideal is not the same as specializing its generators. So let me give you an example here. So let's start with the ideal I being generated by x and x plus zy inside this polynomial ring in 2 variable over, of course, this extended field. Then specializing the ideal also when z gets to 0, right? So here we are looking at z maps to 0. Okay, that is not the same as just substitute z equal to 0 into the generator, because if you do so, then we just get the ideal being x. However, I has another collection of generators which is given by x and y, and for that we actually have the specialization of I being x and y. In fact, for every ideal, there exists at least one collection of generators such that specializations or specializing the ideal is the same as specializing the generators. Unfortunately, that collection of generators is not easy to find in general. What we know, however, is that even though specializations of an ideal is not the same as specializing the generator, it is actually the case for at least when this parameter A is in an open subset of the parameter space. Right? So this is a theorem of Accruals, and it says that if we start with a collection of generator of I, then there exists an open-dense subset of the parameter space such that for every A in that open subset, specializing I with respect to A is the same as substituting A for Z, or specializing the generators. Specialization works well also with intersection and product and additions of ideals. I'm going to mention intersection and product because that's what we are using. Accruals also proves that if you start with two ideals, then there exists an open-dense subset U such that specializing for every A in that. So I should have said for OA in U. Specializing the intersections is the same as taking this intersection of specializations, and specializing the product is the same as taking the product of specialization. Now, this is actually the best that one can hope for, because it's not always true. Right? So, meaning you can't just expect U to be the whole parameter space. And this example, if we start with an ideal X and X plus ZY as before, then when you look at the intersection of I and J and specialize by Z go to 0, you get X squared. On the other hand, if you look at the specialization of I and J, they are both X. So the intersection is X. This is an example where we're looking at ideals in 3 variables, and specializing the product, when you take the product, when you take each specialization, you get x1, x2. So the product of specialization is x1, x2 squared. However, if you take the product of the ideals, there's an extra terms that comes into the picture, x1, x3. So when you specialize the product, you get extra term x1, x3. So they are not the same. Right? So the best one can hope for is to have an open subset that specialization works well. So let's go back to our situation. What happened when we specialize point? So this is the generic point, and its defining ideal looks like this, right? This is the specialized point when we substitute Zij by Aij, and this is how its ideal looks like this. As you can see, to get to this from here, one might attempt to specialize the generators, right? If you just set Zij to Aij, you actually get this, right? So in fact, the new params is obtained from the O-param by specializing one collection of generators. Okay. However, specialization only works with respect to an open subset. So what we get from so here I'm going to let M and MZ be the maximal ideals. So what we get from Accruals result is that for fixed M, R, and L, there exists an open dense subset. U depends on M, R, and L in the parameter space such that for all A in that open dense subset, we have that the specializations of the symbolic M power of the ideal of the generic set of point is the same as the symbolic M power of the ideal of the specialized set of point. And the specializations of a power of the maximal ideal times an usual power of the ideal of the generic set of point is the same power for the maximal ideal times the same power for the ideal of the specialized set of point. So the upshot from this is, if we have containments and inequalities for powers involving a symbolic and ordinary power of the ideals of the generic set of points, we get the same containment and power and equality for powers of the ideals of the specialized set of point, provided that this is in some open dense subset of the parameter space. Okay, and this is the strategy that has been used to prove containments and inequalities. Specifically, Tohanianu and C in 2019 proved that if you look at the ideals for the generic set of points, we have these containments for R big enough. And so when you specialize down, you get this containment for R big enough, which is the stable Harburn conjecture. However, if you every time you specialize, you fix the power, so you have an open dense subset, right? So in order so to make this works for all R, you have to take your parameter inside this intersection of infinitely many open dense subset. That's why their result is that the stable Harburn conjecture hold for a very general set of points. And Fowley, Montero, and C, they prove Chudnovsky's inequalities for the ideals of the generic set of points. Then they specialize down and get Chudnovsky for ideal of set of that lies inside, and again another infinitely many intersection of infinitely many open dense subset, and that's why they get the result for very general set of points, right? So to get the result for general set of point, one has to somehow get rid of these intersections and find one open dense subset that works for all powers. Okay? And if I rephrase the results of Mallara, Schoenberg, and Spahn about Lemaire's conjecture, it's the same idea. They prove the inequality for the generic set of point. Then they specialize down, and once again, because of specializations for all powers, one has to get the result for a very general set of point. So what do we do? What is new ingredient in our work that allow us to get one open dense subsets that works for all power? The technique that we do is that we prove one containment implies stable containment, right? So we prove that if somehow you have one appropriate containment for some constant C, then you get the same containment, stable containment for all R big enough. Okay, and this looks like the simple version of Harburn-Hunicke conjecture. For the strong version of Harburn-Hunicke conjecture, unfortunately, we cannot prove the same thing because we couldn't find the appropriate containment, so containment implies stable containment. What we could prove is that if you have a stronger containment, as you can see that the power here is slightly smaller than the power here. If you have one stronger containment, then you have the desired containment for infinitely many values of R, right? So you can look at R being multiple of this constant C. Okay, and so our method in proving Chudnovsky and Lemaitre is we established first just one containment, one appropriate containment for the generic set of points. Then we specialize that containment down to get one appropriate containment for a general set of points that works on one open dense subset. And using one containment implies stable containment, we get the stable containment for, again, specialized point on one open dense subset. And that established Chudnovsky and Lemaire's conjecture for general set of point. Now, we have a bound in a number of points, and that comes exactly in the first step when we have to establish one appropriate containment for the generic set of point. Unfortunately, there's some combinatorial arguments that we do, and that counting argument needs the number of points to be large. So let me now spend my last few minutes considering a number of examples point configuration that are known to be counterexample to the Harburn conjecture. For example, the first one I'm looking at is the Fermat configurations. So this configuration is the configuration of n squared plus 3 points in P2 given by this ideal inside polynomial ring in 3 variables. Dumisky, Schoenberg, and Tatar-Gazinska later on by Harburn and Ceselenu show that for this ideal, the containment I symbolic third power contained in I square fail. What we could check is that I, the symbolic 10 power, is contained in m to the 6 times I to the 6. And using one containment implies all containments, it implies that we get this containment I to the 2r minus 2 symbolic powers is contained in m to the r times I to the r. And particularly, if you look at, this is an height 2 ideals. So if you look at the statement for the Haber-Huneke containment, this is what we need. That's the Haber-Huneke containment. And there's a variations of the Haber-Huneke containment, which is this containment. As you can see, the trick here is we have to find the right containment. Okay, and it may not be exactly what's given in Haber and Huneke statements. The second configuration is the Brodsky's configurations. B12, this is the collection of 19 triple points lying on 12 lines. Right, so 12 lines intersect at 19 triple points. They also intersect at double points and single point, which I'm not, at other double point, which I'm not, which we omit. Okay, we only consider 19 triple point. And it's known that the idea of this 19 triple point also fails the Haber containment. What we prove is, however, if you look at the asymbolic power of I, it's inside m to the 5th times I to the 5th. So once again, for the stable containment, we have that I symbolic power to r minus 2 is inside m to the r times I to the r. Particularly, we obtain the Haber-Huneke containment. Okay, I'm going to skip through this and move to, oops. Yeah, I'm going to continue with, so let me briefly spend my last 2 minutes saying something about the same kind of inequalities as the Chudnovsky's and the Bayes inequalities, that one can look beyond just points. And so here we look at the determinantal ideal of a generic matrix. Right? So if you let P X be a P by Q generic matrix, and U is any number, and take the ideals of U minor of X, then it's known that this is prime ideals of height being this much. And what we can show is that this containment holds, so the stable, so the actual Haber-Huneke containment holds for this determinantal ideals. Particularly, we have an inequalities like the Bayes inequality for the Warsmith constants. It's also true if we replace a generic matrix by a generic symmetric matrix. So same thing, if you take a generic symmetric matrix and you take minus of this matrix, then we get the same containments, and so the Bayes-like inequality holds. It's also true if we look at determinantal ideal of generic skew symmetric matrix. So instead of, so we look at a symmetric skew symmetric. So this should be skew symmetric. And we look at Pfafffians of ideal of Pfafffians of this skew symmetric matrix. Then once again we have the Haber-Huneke containments and the Bayes inequalities. And finally, let me just put down my last slides here, that if we start with a star configurations, then the defining ideal of a star configurations also satisfy the Haber-Huneke containments, and we have a more general statements with more parameters involved in the powers. And once again, that basically say that the ideal of star configurations satisfy the Bayes-like inequalities. And I think it's time for me to stop. Thank you so much.
Thank you very much, Tai, for your very interesting talk. We are now open for questions from audience. You can use your microphone and also your video to interact with Tai for any questions.
Can I ask a question?
Sure, please. Arindam, yeah.
Tai, you just mentioned about this containment I cube, I third symbolic into I second ordinary. Is much known about I fifth symbolic contained in I third ordinary? Because I know that's also a conjecture people cared about.
Yeah, so you're right. So most of the counterexamples that are known to fail I third contained in I square actually satisfy I fifth contained in I third, right? I fifth symbolic contained in I third. And what we prove is that in most of the known counterexample, the stable containment actually holds. Stable, unfortunately, we don't know from when. But in a lot of example, it actually starts the next, from the next guy, from the fifth power contained in the third power.
Okay.
Yeah.
Tai, I have correspond like this Chudnovsky's and Demaily conjectures. I guess there is a corresponding formulation for monomial ideals, right? One can.
Yes.
I think,
yes.
yeah.
So this is exactly where I get this containment from. As you can see, it's slightly different from. It's slightly more general than Harborn-Hunicke. For example, if you set C to be H, you get Harborn-Hunicke, and this is what we prove for square-free monomial ideals. It satisfies this containment. So that's our earlier work with my earlier work with Susan Cooper, Robert Embry, and Andrew Hoffel. And this is where we get this power from, because it's known to be true for square-free monomial ideals.
Okay, and how is there any scope of improvement in that direction?
So unfortunately not, because actually there are example
Quite
for
sharp.
monomial ideals that fails this containment.
Okay,
So,
okay.
yeah,
okay.
it's true for square-free monomial ideals, but it fails for monomial ideals.
Yeah, I see this in I think it's 9 authors paper where it is proved that for any square-free monomial ideals, this Wald-Schmidt constant is bounded below by alpha I plus E minus 1 by E, where E is the big height.
Yeah, so
Yeah.
actually they fail to realize that actually that result follow from this containment.
Oh, okay.
Right,
okay.
and the containment we already proved. We mentioned it in our paper, but we didn't state it as a result, so they didn't realize that. So,
Okay, so this is kind of I mean, this bound is pretty sharp.
Yes.
Okay.
Yes.
Okay, any other questions? Tai, you mentioned the Harborn-Hunicke conjecture valid for many determinantal ideals.
Right.
So which determinantal ideals we don't know the conjecture?
Well, the types of determinantal ideal that I am familiar with, then we do know the containment holds, right? So we have determinantal ideal of a generic matrix that is known. It's also known for the determinantal ideal of a generic symmetric matrix, and it's also known for the Bafavian ideal of a symmetric skew symmetric matrix. Now, of course, if you start with a matrix that is not generic, then we don't know anything.
Mm-hmm. So, do we know it for height 2 perfect ideal in polynomial ring?
That's a good question. I don't know. I don't think it's known.
Mm-hmm. Because we know the resolution and But
Right.
maybe the resolution, if we could figure out resolution for the symbolic powers, it will probably answer the question.
Right. That's why my first thought is that it should be known, but I don't recall seeing it. So
yeah.
So
What
I
is
think that's a good question to look at.
Yeah. What is the secret behind 4 to the power n?
I'm sorry, the what?
In some of the results you mentioned, you take 4 to the power n generic points.
Yeah, yes. So the idea is that in our method, we always have to look at the generic center point. So that's only one generic center point. And we have to see what kind of containments or inequality we can establish for the generic center point. And unfortunately, for our current technique, we have to do some combinatorial estimations. And that combinatorial estimations require the number of points to be large. So that is so the bound for the number of points is the limit of our technique. It hopefully should be gotten rid of by maybe a different approach, or maybe a better combinatorial lemma than what we had.
Yeah.
There are Thai Jantan here.
Yeah.
There are no results in like binomial ideals or.
That actually is a very good question. So when we started looking for ideals beyond points, right? Determinantal ideals comes naturally, and then star configurations come just because star configuration actually arrive from points. We didn't look or think too much about binomial ideals. I think it'd be very nice to see what kind of binomial ideals would satisfy the same, containment, or the same, or have the same inequalities for the Wadsmith constants. We don't know.
Okay.
Yes. So our technique here is based on some very simple counting problems and understand the symbolic powers very well. So if you have a binomial ideals that you can understand the symbolic powers, then maybe you can try.
Is even the I symbolic 3 and I second power comparability is known for binomial either way?
That I don't know. I haven't seen that before. I know that so there's a recent paper by Drafkin and Siciliano where they talk about various kind of configurations of various kind of example of ideals that fail this containment, I symbolic third contained in I square. But I don't recall seeing binomial ideals in there. So they come from what they call ideals of hyperplane arrangement.
All right. So any other questions for Tai Ha? Well, I don't see any further questions. So, Tai, it's very nice to have your interesting talk, connecting so many different ideas.
Thank you for having me. It's
thanks.
enjoyable.
Coming online. And we can close the meeting again by thanking